one of the things is it helps to think of the different visual channels we can use. Here is a list. I linked the source of this as a PhD thesis that I linked in the materials. You can also find this in Wilke's book. So you have things like length, angle, curvature, shape, area, volume, different aspects of color like brightness, saturation, hue, texture, and then position and like different grouping and things. And so these are like, you could actually come up with even more of them. But so these, if you look at any kind of visualization, usually you can think of the visualization as mapping some aspect to the data to one of these things. So one aspect might be mapped to angle or to area or to color or to the x-axis or the y-axis. One thing that you should keep in mind is, in particular for quantitative data, so quantitative data meaning continuous data, there's a pretty clear hierarchy of these. And there's been several works that study how human perception works and what things work well. So position is by far the strongest cue. So comparing the position of things is much easier than comparing anything else. The second is length, and third is angle, and fourth is area. And so actually this is already quite hard. If you think comparing the area of two things is much harder than comparing the lengths of things. This is a reason why generally pie charts are often considered worse than just a bar chart, because in the pie chart it's using either angle or length, either angle or area, though often it's not, and these are like harder to compare than length. 3D is even harder, and actually color hue is at the very bottom of this hierarchy, and color hue is actually something people love to use because it's very easy to use. And so one of the important things is really don't use color hue for quantitative data if you can avoid it. I very often see in projects people make, like, say, a map, and the map is color-coded or for different frequencies. And so this alone is very hard to read, very hard to compare frequencies in different areas. You can maybe see some hotspots, and we'll talk about mapping from a continuous number to colors later a little bit more. But there was one plot that someone showed me that was I think 2 maps of New York colored differently about bike ridership, and they showed me that one is the women and the other one is the men, and they told me there's particular ratio that you can see. But personally, so if I have 2 images, I cannot compute the ratio of the hues in my mind. If I have the ratio of length, I can maybe sort of do that in my mind, but doing any calculation on color hues is basically impossible. And so I would, if there's a critical aspect of the data, don't encode it as a color hue for quantitative data. Here is an illustration that I think is nice from Wilke's book, which shows how you can think of different aspects of the data mapping to different of these channels. So this is like a fuel efficiency data set, and so we're showing a 5-dimensional data set here. It's a very small data set, so we can show all of it, but it's 5-dimensional, and actually all 5 dimensions are shown in a 2-dimensional plot. So displacement is mapped to the x-axis, fuel efficiency is mapped to the y-axis, horsepower is mapped to the hue, weight is mapped to the size of the of each point or marker, and cylinders mapped to the shape of each marker. And so here, this is sort of, I think it's very interesting to see how you can combine all of these different axes. So combining all of these probably in practice will be a bad idea. So usually you will have much more data and will be much too crowded. Also, it's sort of hard to perceptually comprehend all of these at once. But I think it's nice to see about like which of these channels do I want to use and which axis do I map to which channel. So in this graph, I could probably equally use the displacement as the color and the power as the x-axis. That would get a completely different chart. And so it's important to think about what are the things that you really want to visualize and which mapping to the different aspects of the chart brings it out best. So talking a little bit more about colors, whenever you visualize a continuous variable, like using color or brightness or hue or saturation, you're using a color map that goes from 1D continuous value to a color. Here are some of the color maps in Matplotlib. And actually the choice of the color map is quite important. So if you have a qualitative variable, a categorical variable, you will want a qualitative color map, which is sort of obvious that you want things that are like discrete units. But if you want to have a continuous variable, there's all of these different choices. And historically, led by the amazing MATLAB from MathWorks, I think, people use this color map jet. And there's actually quite some issues with using a color map like this that I want to go into. But so there's generally more or less three kinds of color maps. So there's those that are sequential, so that go from either from light to dark or from dark to light, and then also change in color. There's the diverging ones that have like a midpoint, so that's usually like 0 or neutral or something like this, and then I go to both negative and positive. And then you have these that are sort of mixed high contrast color maps. And so even though these were used a lot, there's actually in a lot of areas quite an issue. So by default, I think Matplotlib and many other libraries now use the blue one here. It's called Viridis. There's also a couple other ones, Inferno, Plasma, and Magma, that are what's called perceptually uniform. And so I want to briefly talk about what that means. I think I also linked in the course material to a really great talk by Stefan van der Walt and Nathaniel Smith. They both worked on developing this color map. Usually they both work on NumPy. So here are, on the right-hand side, you can see 3 images. And these are, oh, my mouse pointer is somewhere else. There's here 3 images. These are 2D images that we map with a color map. Here in this case, it's the gray color map. The gray color map you can see here. It just goes from black to white, and basically with a uniform gradient. So the weighted lightness changes is uniform. So color maps are in particular important for heat maps like this one here. So if you have a 2-dimensional array and you visualize each pixel as a number, basically it's a heat map. And so here's a comparison of on the left the jet data, the jet color map that used to be used in Matplotlib and many other places. And on the right-hand side, you can see the Viridis color map, which is the default since Matplotlib 2.0. And so what people notice is that with the color map on the left, with the jet color map, if you look at these two in particular, you can see that there looks to be like contours around the red and the yellow that are not actually there in the original data. So here this looks like just like a blob, whereas here it looks like there's a very clear ring, and here you don't see that ring. This sort of effect of having these discrete rings comes from the color map having very different changes in the gradient. So what you can see both here and at the bottom is the colors mapped in a three-dimensional space that corresponds roughly to what the human perceptual space, so how we perceive contrast between colors. And you can see that in this space, there's a bunch of kinks in how this one-dimensional continuous number is mapped to the colors. And if you look at the gradient, this guy is the gradient of the color map. So basically, if you compute the gradient of this guy here in the space as it is perceived by humans, you get this. And this seems a pretty terrible way to map a 1D scalar, right, to anything. And that is the reason why you get these ring effects. When I first gave this lecture, a lot of people were still using these kind of color maps. Now people are less and less using these kind of color maps, but hopefully sort of I gave you an idea why. And so it's quite important that if you use a heat map, that you use something that's perceptually uniform, otherwise you might get these artifacts. And like, if you look at the data set, this plot and this plot might lead you to very different conclusions, and so just artifacts in the color map might lead to drawing conclusions that are not there. Oh yeah, and then another fun thing is, if you print this to black, or if you convert it to black and white, it's not invertible and it's completely garbage. So it's like completely non-interpretable because it goes from dark to gray to a little bit lighter to a little bit darker. Anyway, so these were just some notes on general visualization principles and how to think about them. I want to now transition to talk a little bit more about Matplotlib. And I'm talking about Matplotlib version 2 and 3. I hope no one is still using Matplotlib version 1. If you're using Matplotlib version 1, just don't. Ideally use version 3. So all the new styles and defaults, they changed a lot of things between 1 and 2. You should definitely be using 2 and better use 3. So before I talk about Matplotlib, I want to talk about some of the libraries in Python. So Matplotlib is the one that's been around for the longest, and that has most of the most things built on top of it. So in particular, the plotting in pandas is built on top of Matplotlib, and it's quite convenient if you're plotting from data frames, or generally it's pretty convenient. There's also Seaborn. Seaborn is built on top of pandas and Matplotlib. So if you use any of these, the pandas or the Seaborn one, it's very good to understand the fundamentals of Matplotlib because that's what it's built on. Seaborn has a lot of ready-made stats plots that can be quite useful, though I find for the kind of data that I have, they're sometimes a little bit cumbersome. But yeah, your mileage may vary. But it definitely has much more ready-made plots like violin plots and like facet plots and small multiple plots that are not easily built or they're like a little bit annoying to build in Matplotlib directly. And then there's a couple of alternatives. So probably, I think by now, the most commonly used one are Bokeh and Altair. Bokeh and Altair are basically from ground up complete rewrites of the visualization. And Altair in particular is declarative, and basically you declare the data structure and you declare in a data frame what axis you want to map to what aspect of the figure, so the x-axis or the color or the y-axis or the scale or so on. So it very much goes after this principle of mapping like columns in the data to aspects of the figure very directly. And so that's kind of cool. It's still a little bit new, and I'm not but it's getting more and more complete. Bokeh is also from the ground up rewritten. I think both Bokeh and Altair might only work in Jupyter. So you can't, I'm not sure if you can use them. Well, you can probably use them in standalone scripts, but I'm actually not entirely sure how well they work in standalone scripts. They're mostly meant for in browser. Yeah, so Bokeh is another library rewritten with JavaScript support. Both of Altair and Bokeh are pretty good if you want interactive visualization in the browser. If you're coming from R, there are several ggplot translations and interfaces and transcriptions, so you can check. I think plot9 is maybe the most current one, but there's like always new ones coming out. And they're always missing something, so someone else comes up with a different one. There's bqplot from Bloomberg. That's quite good for doing interactive exploration of time series. So this is also like JavaScript based in browser. So you can use it from Python, but it's written in JavaScript. And yeah, it has a focus on time series, as you might expect for a financial institution or financial company. Finally, there's Yellow Brick, which is also written on Matplotlib. Yellow Brick is for plotting particular aspects of scikit-learn. So it tries to do some things for easier model visualization and metric visualization. Right now we're working on putting more visualization directly into scikit-learn, and so maybe we'll sort of absorb the stuff in Yellow Brick. But for now, you can either use the stuff in scikit-learn that we're just creating, or you can use Yellow Brick, or you can roll your own using any of these. For the first homework, I require you to use Matplotlib. For all the later homework, you can basically use anything you want. Though you're not, I'll say this again in the homework, but I don't think there will be any homework where you're allowed to use Dabble, which is my new library because it does everything automatically. And I want you to understand what's happening. Yeah, so I mean, I'm basically using Matplotlib-based plotting, but if you prefer Bokeh or Altair, Plotly is also an option. Plotly is done by a company. I'm not sure how much of the library they're completely open sourced by now, but there are some aspects that are proprietary, but a lot of people like it. Anyway, so I'm going to talk about Matplotlib. First off, imports. Please don't import star even in a notebook, particularly because a lot of the fundamental libraries might have similar functions, like histogram. If you do this and you call histogram, what is it going to do? It's kind of hard to know, so please always import these things as like a module. Second thing, so I don't think you have to actually do this in the most common Jupyter lab anymore. Oh, maybe. So he here knows the difference between Jupyter Notebook and Jupyter Lab. No one, okay, who here has used Jupyter Lab? Okay. Who here has used Jupyter Notebooks? Oh, okay, I'm going to tell them that they need to work on their marketing. No, so Jupyter Lab is the next generation of Jupyter Notebook, basically. So where you have, at the side you have like a file browser, and you can open like multiple windows at once, and you can split them, and it's much more like an IDE. And so I guess they wanted to have some of the nice aspects of IDEs, like what you get maybe in RStudio or in Matlab, and like be a little bit more like that. Jupyter Lab is great, try it out, but I'm not really going to talk about it anymore. So if you want to plot in Jupyter Lab or Jupyter Notebook, you used to have to declare that you want to do Matplotlib inline, but I think now they do this by default. What this does is basically it renders a PNG, so you just render an image and you send that image to the browser. That's very robust and it just kind of works, but it means you don't have panning or zooming, and it also means every time you do a call you get a new figure, and you can't change a figure that you created earlier because it was just a PNG sent to the browser. And so that's sort of nice and easy, but it's like pretty static. If you're in Jupyter Notebook, you can do Matplotlib Notebook. That gives you interactivity, so then you can do pan and zoom. Oh yeah, this is a notebook magic. So this is a Jupyter-specific command that starts with this %. So if you do everything that starts with a % is a command that goes directly to Jupyter. And so this tells you want the notebook interface for your Matplotlib Notebook. This is JavaScript based and doesn't work in Jupyter Lab. But it works in your Jupyter Notebook, and so this allows you to update existing figures, and it allows you to have like interactivity, and you can do pan and zoom. By default, Matplotlib doesn't have any brushing, which many of the other libraries do. And finally, if you're using Jupyter Lab, which you absolutely should, and you want interactive visualizations, you have to run Matplotlib widget, but you have to install a plugin. So in Jupyter Notebooks, basically the notebook could include arbitrary JavaScript and would just run it. That's a pretty big security risk, and so they stopped doing that in Jupyter Lab. And so in Jupyter Lab, basically, so they can't just push the JavaScript anymore, so you have to install a separate package that contains the JavaScript for the interactivity. All right, so now we finally have set up imported and set up our Matplotlib. Very briefly, some terminology. So the two main objects that you're working with are figure and axis. The figure is usually like one window if you pop it up, or one image file, or one interactive thing in the browser that has its own like GUI. And an axis is a drawing area that has its own coordinate system. By default, if you call plot, what will happen is it'll create one figure, and the figure will have a single axis, and you'll plot into this axis. But very often it's nice to create multiple axes within the same figures if you want to do small multiple plots or something like this. So here you have two axes within a single figure. So there's a couple ways to create figures in axes. So the first way is you just don't worry about it. If you call any plot command, it will create a figure in the axis for you, and it will plot into this figure in the axis. You can do plt.figure, it will create a figure, it will have a single axis, but you can add other axes later. Or my favorite way to create axes is plt.subplots. That allows you to get a regular grid of n times m of subplots. So this is sort of what you get here. Here I have got like called subplots 2,2, so I get a 2x2 grid, and then I can plot into each of these things individually. So if you really like MATLAB, there's one way to create a similar thing, which is just called plt.subplot nmi, where n and m is the shape of the grid, and it will add something to the ith, and you will get the ith element of this grid back. This is kind of a weird interface. So here at the bottom I wrote, like, if you do 221, you get the top left. If you do 222, you get the top right, and so on. And it's indexed by 1 because it's stolen from Matlab. So I prefer doing something like plt.subplots 22, and I get the figures and the axes back, and I have an array of axes. The benefit of doing this one axis at a time is that you can be a little bit more creative, and you can add axes of different shapes. So here, for example, for the first two plots, I pretend I have a 2x2 grid, and for the last one, I pretend I have a 2x1 grid, and so I can have like a row spanning axis, and I can do cool plots with that. The main reason for like having these two slightly different interfaces for subplots, though, I think, is that there's generally two interfaces to all of Matplotlib, basically. One is a stateful interface, and the other one is an object-oriented interface. So in the stateful interface, there's a current axis and a current figure. And if you call any plot object, it will plot into whatever is the current object. So there's a global state, which is like, if you're a computer science person, like, it makes you slightly nauseous. And so basically the user has to remember what is the current global state, and this is what I'm going to plot in. This is if you call plt.something, this is the interface you're using. If you call plt.subplot, it'll set the current axis. So it will create an axis and set the current axis. So, for example, I can say, oh, I'm going to create the subplot in a 2x2 grid at position 1, and then I'm going to plot into it. And I'm going to create it at the position 2, and I'm going to plot into it, and this time in red. And so this is the two plots that you can see. So this is a stateful interface, where basically there, somewhere in the depth of Matplotlib, it is hidden which one is the current axis. The interface that is much more explicit is the object-oriented interface, where basically we have axis objects, and on the axis objects, so actually this axis here is a 2x2 numpy array of axis objects, and I can index into it, and then I can get out the single axis, and I call the plot command on the axis. So here there is no hidden state, and I say explicitly what is the axis I want to plot on. So these two codes are equivalent ways, only they use like very different interfaces in a sense. So sometimes when I do quick and dirty stuff, I use like, if I want to do a single figure, basically, usually I use the first one. If I want to do more than one figure, I usually use the second one. But generally using the second one is sort of much cleaner, where you explicitly handle which axis object you're working with. And I think the difference between these two interfaces is sort of a main pain point in using Matplotlib. And so it's good if you sort of think about that a little bit and make sure you understand it. So, because if this would be the only difference, that would be too easy. So all the plot commands, like plot and scatter and histogram and I don't know, bar, all of them have the same name in both of these interfaces. So you can do plt.plot or x.plot, or you can do plt.bar or x.bar. But anything that modifies the axis has different names. So plt.title is the same as axis.setTitle, plt.xlim is the same as x.setXlim, and so on. And some of the things are only available in the object-oriented interface. For example, setting the ticks and the labels differently. And there's some other things that you can do only in your interface. But so, depending on whether you use the stateful interface or the object-oriented interface, you have to prepend the set underscore or not. which is definitely not confusing. Oh yeah, and if you wrote, let's say, if you wrote something, but then in the end you figure out, oh, I want to change something on an axis I created earlier, or you can always get the global state objects with plt.gca to get current axis or plt.gcf to get current figure. This will give you the objects that are the current objects, and so that's also often useful. I briefly want to talk about some of the most common plot commands and some of the nice things and tricks about them. Matplotlib has a gallery that you can find at the top, and there's also a great summary which has all of the high-level plotting commands. The first one is plot. So plot you can use for line plots and for scatter plots, basically. So by default it does a line plot. If you don't provide a y-axis, it will just enumerate. And so here I just gave the x-axis. If you don't give it an x-axis, if you give it a single array, it assumes the array is the y-axis. So if I give it just a sinus curve, it goes basically, it enumerates the values. So there's 100 values and it goes from 1 to 100. I can also explicitly give the both the x and the y-axis. So if I give two arrays, it's the x-axis and the y-axis. And then I can also change them. If I want to do a scatter plot, you can change the markers. So by default, it's a line plot. If I set the marker instead of dash, which is the default, dash means a line plot. If I set it to O, I get a scatter plot. If I set it to dot, I get smaller scatters. If I set it to X, I get a scatter plot with X's, and so on. Of course, you can set things like color, transparency, and so on. If you want to do a line plot with dashes, you can set to dash dash. If you want dashes and dots, you can do dash dash O, and so on. So there's many different line styles. One thing that I'm a little bit angry about is that, so in PLT that's subplots, you can specify the figure size, which is often good, because if you don't specify the figure size, the figure will have some default shape and it's usually bad. So if you see the subplots called 2, 4, which means there's 2 rows and 4 columns. So it's y, x, but then the figure size is x, y. And then I get angry. Cool. So another command that's very useful is scatter. So scatter can do scatter plots. Plot can also do plots, scatter plots. So here, the first one is just calling plot with O. The second one is calling scatter with X and Y. They're the same. But what scatter can also do is you can change the color. So if you either want to do a continuous variable or if you want to plot categorical variables like color by class size, you can, or by class identity, you can set C. In this case, I set C to be the difference from the diagonal, and I use the contrasting color map, so everything that's on X equal to Y is white, everything above is blue, and everything below is red. So scatter can also set the color individually for each point, and can also set the size individually for each point. If you don't want to do that, then plot and scatter do the same thing. New in Matplotlib 3, I think, for some reason, is you can also have legends for scatter plots. But it's like a little bit annoying. Histograms, also great. by default, histograms have 10 bins. That's never the right number of bins. So you can change the number of bins manually, or there's auto. You have the same auto keyword if you use the histogram from pandas. The histogram from pandas just calls this, which calls the NumPy histogram, and NumPy has the auto option. So there's several different heuristics for finding the bins, but basically it usually looks much more reasonable. You can probably do more fine-tuning or do more statistical analysis, but basically there's not really any reason to use 10, and auto is probably going to be better. Okay. Bar charts. I don't know if there's anything interesting. So bar charts actually, I think, are a little bit easier to do if you use pandas directly, and with Matplotlib and Matplotlib, you have to give it both the, in this case, the x coordinate and the height. So I give it the range and then the number. For horizontal bar charts, again, you have to give it the y and then the width, which is annoying. And so pandas would make these for you automatically. So generally, if you have very long categories, okay, so these two charts are the same. Who finds the one on the left easier to read? Who finds the one on the right easier to read? Okay, so I also find text much easier to read if it goes from left to right and it goes from bottom to top. Even if I make it from top, is it from the bottom to top or? Yeah. Even if you make it from top to bottom, that would maybe be a little bit better. But I think left to right is really, at least for, people that are mostly used to English, it's easier to read. And so if you do horizontal bar charts, you can make the ticks in a reasonable orientation. Very important trick. So whenever I have many categories, and long category names, I would always use a horizontal bar chart just so I can read the tick labels without doing this guy. Cool. Yeah, heat maps. I mean, so as I said, for heat maps, one of the there's two things that are actually interesting. One is interpolation. The other one is thinking about the color maps. So I already talked about the color maps a little bit. So at the top left is the default behavior, at least in the new in the version 2 and 3. So you can interpolate maps. Sorry, so you can interpolate heat maps. That's on the top right. People sometimes like to do this because it looks nicer. But what you're doing is you invent data mostly. So don't interpolate plots unless there's a good reason to. So they used to do this by default, now they don't. But if this is actually your data, and your data is this, then I don't think there's a reason to show this instead. If your data came about by some aggregation or something that makes smoothing sensible, I don't know. Maybe, but definitely something to think about. And then, so the choice of the color map also matters. So, for example, both in this default one and in this one, it's very hard to figure out the value of the background. So I can see that where it's bright and where it's dark, but I don't know, I might be interested, is the gray positive or negative or 0? And I can't really say, is the gray positive or negative or 0? And I can't say it in the top one either. So here, this is a good example for a diverging color map, where I can see where is the 0 level and what's positive and what's negative. Oh, another thing that's interesting when using color maps is specifying Vmin and Vmax. These are the maximum values for the color map. So otherwise, the color map gets scaled by whatever data is available, but if you know sort of what are the reasonable minimum maximum values, then maybe you can see more detail, or you can look at different aspects of the data by setting different vmin and vmax. All right, so coming to my favorite issue, overplotting. So usually when you do machine learning, you're happy if you have big data sets. That's slightly different to sort of more classical data visualization. Most like data visualization that is like 60s, 70s, 80s, 90s, they didn't have a lot of data. So they didn't really think about overplotting too much. So here I have this plot, and so on the left-hand side, you can basically see very little about the structure of the data. And so the easiest hack that a lot of people use is to change the alpha. So if you change the transparency, you can maybe see more structure of the data. One issue here is that it's actually, there's not necessarily a right alpha value. So here I created the data so that basically all of the mass is in the center. And depending on what the alpha value is that you chose, you can see this or you cannot see this. Or you might not see other aspects of the data. Anyone have an idea what another way would be to overcome the overplotting issue?
Add some noise. I like a little bit of noise so that the points don't fall directly on top of each other.
One way is to add a little bit of noise, but that mostly actually works for things that are ordinal. Here, this big stripe in the center, there's just like, you're just going to make the stripe wider if you add noise, right? So that's not going to help.
If there are enough points, you can just plot random points as long as the distribution looks fairly similar. Okay,
yeah, you can plot random points. That's also a good hack, not what I thought of, but that's definitely also a solution. So what my favorite thing is hexgrids. What hexgrids do are basically 2D binning. And so what you're doing is you compute a density map. It's called hexgrids because you're binning not on a rectangular grid, but you have like hexagons, and they're like in a honeycomb structure. You could also do this on like a regular 2D grid, but the main idea is that you're just visualizing density directly. So here now, if I visualize density directly, I can more readily map the density to a color map. Again, I said earlier, well, mapping a number to a color map is maybe like not the best idea, but it's still better than dealing with the overplotting. And so here you can see I actually set the bins to log. So basically I did this 2D histogram on this honeycomb pattern, and then I took the log of the densities, and then I plotted that. And so what you can see here basically means that the center point has about 10 to the 4 many points, and everything else has like 10 points at most. So like all the data is in the center. And it's actually very common that sort of if you look at a plot, it looks like the data is everywhere, but actually most of the data is very concentrated in a couple of few points. And so I think this is actually quite a nice technique to work with bigger data sets. Oh, there's another one that I should have put on the slides but didn't. There's a software called Data Shader for bokeh, but there's also a Matplotlib version. I'll post a link to it, which basically uses every single pixel as a different bin, and it's also kind of cool. But yeah, so this is sort of going from scatter plots to density plots is one way to overcome overplotting. There's actually like a whole big literature on how to do this in the plotting literature, but I don't think there's like a real consensus. I mean, subsampling is definitely also an option, and then there's like splatter plots and some other things. But I think if you like basically changing alpha is like maybe nice as a first approximation. It's usually what I do as like a first hack, but then looking at density plots can give you more resolution. All right. So the next thing that I want to mention is twin axes. So here, in this plot, I'm comparing two things. So I have two series. One of them is the number of math PhDs awarded for each year from 2000 to 2009. And the other series is the revenue that was made by arcades in that year. And so let's assume I think they have something to do with each other. If I just plot them sort of naively using plot, they will both share the same y-axis. And so, wait, can I do powers of 10? This is billion, right? It says something like, yeah, they made like $1 billion or something in 2000. And so that's obviously way, way higher than the number of math PhDs. So the math PhD line just looks like a flat zero. The way to fix this is to add a new x-axis that has, use twinx. Twinx uses a twin of the x-axis, but adds a separate y-axis. And so now I have a separate y-axis for the revenue by arcades and one for the number of math PhDs. And you can see the math PhDs are like in the thousands, and the revenue made by arcades is still in the like around 1 billion. And we can see that they're highly correlated, and it's definitely like I think it's p with like the p-value is like 3 zeros at least. But I mean, they're causally unrelated, but they're statistically correlated. So yeah, this is something if you want to compare different series using twinx or twiny, if you want to do it in the other direction, is very useful. A couple of other things more in terms of guidelines for creating the plots you should think about. One is aspect ratios. So there's actually this cool blog called eagereyes.org. They have a couple of cool things about visualizations. So there was a thing in the vision literature, I think it was like maybe in the 90s, where basically it said, well, so the question is, what is the perfect aspect ratio? So these three plots show the same data, but you could interpret them as telling three different stories. So in the first one, or let's say in the second one at least, the June spike is like very pronounced and looks like, oh, something happened in June, whereas in the third one, you would never say, oh, something happened in June. And so interpretation clearly sort of changes with just how you scale your axes. Matplotlib has a default, and it just uses the default. And there's no reason why this default should be the right thing to do. There's a thing called banking to 45 degrees. And basically, the idea behind it is computing all the slopes and then change the aspect ratio so that the mode of the slopes is 45 degrees. And there was like a usage study actually done saying this helped, but then it didn't replicate. So this is still something people do, even though the science didn't really like confirm. But it might still be like an interesting thing. I'm not sure if there's something in Python to do this right now, but and I'm also not sure if it's like the right thing. But it's definitely something to pay attention to when you're creating your plots. Similarly, baselines are quite important. So here, again, the same data plotted in two different ways. And again, the message can be very different depending on what your baseline is. So people often feel like baseline 0 plots are sort of the honest one, but it depends. And so for each of these choices, whatever plotting library you use will have a default value, and it will do this thing for you. But there's no reason the default value should be the right thing for whatever your visualization is. And so it's basically just a choice that you need to make, but you just should be consciously making this choice and not just doing whatever the library did for you. All right. So you can also plot in 3D with Matplotlib, but so if you want to plot with 3D, you can import from MPL toolkits, MPL 3D, import axis equal to 3D. You just need to import it, you don't do anything with it. And then if you create an axis, you need to see projection equal to 3D. If you have an interactive axis, you can spin it around and pan and zoom and everything. If you do the PNG front end, obviously you don't have any activity. And then you could, for example, you can specify a viewpoint in a projection if you want. So here, I think this is like a Lorentz attractor or something. Oh yeah, it says so. That looks really cool, just doing a line plot. Generally, I find 3D things not as useful. In particular, I mean, if you don't have the interactivity, they're just pretty useless because, so if you do, for example, a 3D scatter plot, without interactivity, it's just a 2D scatter plot with a weird projection that the UI chose for you, right? If you have the interactivity, you can spin it around, you can see different angles, but at least sort of for, it might be good for exploration. Honestly, I don't do it that much because usually you don't have only 3 axes, you have like 50 axes, and if you have 50 axes, then whether you can show 2 or 3 at a time, maybe it doesn't make that big of a difference. But yeah, you can do like all kinds of different 3D things.